All right, so this problem follows up with yesterday's lesson where we were solving square root functions, but this one's actually going to take us even a step further in what we end up doing with it. We do start like normal, so I'm going to go ahead and add that 4 to both sides. Because I always want to isolate the square root first, and I isolate the square root so that I can then get rid of it by squaring both sides of the equation. It's just that in this case, when I square both sides of the equation, the right side is not quite as simple as what it's been in the past. I'm actually going to be doing x plus 4 squared. And if I'm going to be doing x plus 4 squared, yeah, I'm going to have to multiply that out, as you're going to see. So remember that doing x plus 4 squared means doing x plus 4 times itself. And so I go ahead and multiply everything in the first parenthesis by everything in the second parenthesis. And it gives us this. X plus 6 equals x squared plus 8x plus 16. So the reason why I wanted to multiply that out is notice now I have a quadratic that involves both x squareds and x's. And so now I can solve it using the methods that I've had in the past for solving a quadratic, which is set it equal to 0 and then solve from there, hopefully by factoring, possibly by quadratic formula if it ends up being harder. All right, once we've set it equal to 0, we look to see, is it factorable? Because that's certainly going to make it a lot easier if it is. Is this one factorable at this point?
Yes.
Yes. And how do I know? Remember that if it's just a plain old x squared, there's nothing in front of the x squared here. All I have to do is look to see what numbers add to the middle number and multiply to the last number. And of course, to add to 7 and multiply to 10, that's got to be 5 and 2. So 0 equals x plus 5, x plus 2. Set each of those individually equal to 0 to see what x equals. We find that x equals a negative 5 and negative 2. Now your assignment last night did not have anything quite this complicated on it. So perhaps, because we've only done 1 or 2 like this even together in class, it might be tough to remember that there is actually one more step here. Remember, the rule is that if you have an x on the inside of the radical and an x on the outside of the radical, you need to check your solutions. So we now need to take my x equals negative 5 and plug it back into the original equation to see if it works. And then take the x equals negative 2 and plug it into the original equation to see if it works. So that's your first line of your check, and then you're just going to figure out what it equals. Remember, don't move stuff left to right, just figure out what it equals on each side. All right, so now I'm going to go ahead and do that check, and when I do so, all I'm doing is just following order of operations on this left-hand side here, because that's where there's actually calculations to be done. So negative 5 plus 6 is 1, square root of 1 is 1, 1 minus 4 is negative 3. If I start doing algebra, like trying to move this 4 to the other side or something like that, I'm doing the very things that might cause the extraneous solution to appear in the first place. And so I don't want to do that. It's just doing order of operations. Never crossing the equal sign so that we can see if the left does equal the right or not. So the first one in this case, negative 3 does not equal negative 5, so that one is going to be not a solution. Remember, we call that an extraneous solution. Extraneous, extra, starts with the word extra and extraneous. So it's an extra solution that's not really a solution. Now let's check the negative 2. Again, you plug it in for x wherever x appears. In this case, there's 2 of them. So I plugged in negative 2 twice. And then again, just do the math on the left side. And the right side, well, there's no math to do. It just stays a negative 2 all the way down. And in this case, when I do that work, I end up finding that negative 2 does equal negative 2. So that one checks out. The left did equal the right, so that is a solution. And so my final answer here is that x equals a negative 2. And that's it. That's the only solution. The negative 5 disappeared. It was extraneous. One other thing I do want to mention on these, we've done a couple of these where we had to check solutions so far, and in both of those, one of them has not worked and one of them has. That is not a guarantee. It's not a guarantee that one will, one won't. Sometimes both solutions will work, and sometimes neither solution will work. So all of those are possibilities. So even once you find the first one, whether it does or doesn't work, you still got to check the other one too, because we still can't make a conclusion about it without checking it. All right, shifting gears into today's new material, we're going to be working with what we call rational exponents, which ties very closely to radicals, as you'll see. I'd like you to start by taking a look at each of these values and see, can you find each of these values, each of these cube roots, without using a calculator? Take a few moments, see how many of them you can figure out. Now as you're doing these, remember what a cube root means. When I see cube root of 8, what that really means is what number times itself 3 times equals 8. That's what cube root's really saying, is what number times itself 3 times is going to equal 8. All right, now the nice thing is that for these, because I say you can do them without your calculator, you know they're going to be whole numbers. Since it's multiplying by itself 3 times to get that number, then you know it's got to be smaller than that. So a number smaller than 8. So I'm going to start really low. I'm going to start with 2. What is 2 times 2 times 2? Well, the 2 times 2 is 4, times 2 is 8. So the cube root of 8 then is 2. Okay, next up, number 2. What is the cube root of negative 8? Really the question here is, does the cube root of negative 8 exist? Well, let's check. What if I made each of these 2's up here negatives? Well, what's negative 2 times negative 2? Yep, that's a positive 4. And a positive 4 times a negative 2 is negative 8. So yes, it does work. I can't do a square root of a negative, but I can do a cube root. The general rule is that if it's an even root, we cannot do it of a negative. An odd root, we can. And so the cube root of negative 8 is negative 2. Okay, so what's the cube root of 27? Well, 3 times 3 is 9, times 3 is 27. So yes, that does work. It is 3. The cube root of 64. Yeah, 4 times 4 is 16, times 4, yes, is 64. So yes, that's 4. These numbers get pretty big pretty fast, right, when we cube them? So what number cubed equals negative 125? It's got to be a negative, and yes, it's 5. All right. Now, how could you know those? Well, really, it's a matter of knowing these values. These are really ones that you should know going forward, which means that really should probably go into your notes here. This is a list of different numbers, different powers you should memorize. We're not going to worry about getting too crazy with too high of numbers at the moment, but you should know at least these. And then although you're writing these into your notes right now, you will find that they come up often enough that you really will need to memorize them. So be working on getting these down to where you just know them by heart. One to point out in particular, just make sure you know what I'm talking about here, this 1 to the n. N is any number basically here, because 1 to the power of anything is going to give us 1. Now we are going to be working a decent amount with exponents today, and so I want to bring back some of the basic rules from way back in the day. So I'd like you to please simplify each of these 3 expressions. All right, so let's take a look at each of these. I'm going to show you kind of the long way of why these rules are what they are, because many of you remember the rules, but probably cannot tell me why they're the rules. So it's always good to remember where they come from. This a to the 4th, a to the 7th. A to the 4th, remember, means a times itself 4 times. And a to the 7th means a times itself 7 times. Well, now you just got a whole bunch of a's all multiplied together, right? How many a's do I have multiplied together? 11. Notice in order to get that number, all I had to do was add my 2 exponents, the 4 and the 7. All right, we can take a similar approach to seeing why we do what we do when we divide. Because if I have n to the 5th, that means n times itself 5 times. That's over n to the 8th. So that is 8 n's on the bottom. And then to simplify this, I start canceling out pairs of n's from the top and bottom. Notice what I'm left with. I'm left with 3 n's all multiplied together on the bottom, which means n cubed on the bottom. Now if I canceled out everything on the top, that means I'm left with just a 1 up there. So what's our rule? Well, technically what we're doing is we are subtracting. I'm doing the 5 minus the 8, which gives me a negative 3. And a negative exponent always means to put that exponent on the bottom. So that's why the n to the power 3 is on the bottom of the fraction, and why we can also see why it goes on the bottom when we do that canceling thing. All right, and finally, y cubed to the 4th. Well, y cubed to the 4th means, well, y cubed is y times itself 3 times. And the 4th power means to multiply that by itself 4 times. Notice what I have here. I have 4 sets of 3. So if I want to know how many total there are, I do 4 times 3, which is 12. Notice I multiplied those exponents. And that's why multiplying the exponents is what it is when we have a power to a power like that. So those are the basic rules that we would have seen before. Today we're adding one that's not quite as simple. Today we're adding in fractional exponents. So here we can see the general rule. This is actually the basic rule. X to the 1 over b equals the b root of x. So for instance, x to the 1/3 equals the cube root of x, that sort of thing. But of course this rule only works if it's a 1 on top, right? So this is actually a special case of another rule. It's just a special case of this particular rule. It's just the case where a is 1. Both are probably worth writing down to your notes, but really this is the one that represents them both. So now we're going to practice using that new rule. So these are telling us to write each expression in radical form. That is, take the fractional exponent and rewrite it as a root of some sort. All right, so x to the 1/2. We know that anytime I see the fraction in the exponent that I'm going to a radical, right? All right, so the number that is the root is the bottom number. So this is the second root. And it's of x. Now I could also write x to the 1 there if I wanted, but I don't need to. Now, the thing is though that I don't normally write it like that. The second root is also called the square root. So of course you don't need to write the 2 in there. And x to the 1 is just x. So x to the 1/2 power equals the square root of x. That is well worth noting and remembering, because that is kind of the most basic version of these problems. But it's also, in some ways, one of the hardest to see because the 2 and the 1 don't get written in. So it's well worth memorizing even on its own. All right, the next one, x to the 24/3. There's actually a little trick to this one though, which is why I've thrown it in, because I want to make sure you're looking for this trick. Notice that fraction can be reduced. What does 24/3 equal? Yeah, it actually just equals 8 over 1, which is just 8. Well, x to the 8, that's just x to the 8th. I don't need to do anything extra fancy with that. I can just go ahead and give that as my answer, x to the 8th. All right, and then this last one, x to the 3/4. That fraction does not reduce, so we can't do anything special there, so I know I got to go to radical. Which root is this? Is this the 3rd root or the 4th root? 4th root, yes. The bottom is the root. And so then inside is going to be x to the power of something. It's always x to the power of the number on the top, that is the numerator. So it's got to be x to the power of 3. That doesn't reduce in any way, so that's our final answer. That's what it is in radical form. All right, now these problems were given radicals and we're told to write them in exponential form. I will tell you, typically speaking, if you are doing a problem and you have to decide, do I leave it with a fractional exponent or do I leave it with a radical? You'd rather actually have this form. But there will be times, as you see, when we need to be able to go this other direction, so we're going to practice it for that. All right, so we're taking the cube root of x, and I know that if I'm taking this and getting rid of the radical, I'm going to have x to the power of a fraction. I like to start with what goes on the bottom of the fraction, because the bottom of the fraction is the root. This is the third root, that is the cube root, so it's going to be over 3. But it doesn't say what number goes on top. So what number does go on top? 1. Yep. If it's not written, it's the 1 there, at least on top. All right, so then that's our final answer. It is just x to the 1/3. Okay, next one. The fourth root of x to the 8th. Again, I'm going to go to a fraction, x to the power of. Which number goes on the bottom?
4.
The 4, yep. And which number goes on top?
8.
Yep, whatever the exponent is. Now notice though in this case, that can actually simplify. My fraction, 8 over 4, yeah, that just equals 2. So that ends up equaling x squared. So you go through those steps, and anytime you see that fraction, look to see if it can reduce. All right, and then this last one. Again, I start with a radical, so I know I'm going to end up with x to a fraction. Which number goes on the top of this fraction?
2.
2, yes. I did it in different order, seeing if I could throw you off. And so which number goes on the bottom must be the 5. And so it's x to the 2/5. Can I reduce that fraction at all?
Nope.
Nope, that's as good as it gets. So then that would be our final answer in exponential form.